Now we talked about the first fundamental theorem of calculus. I'm going to just call it fundamental theorem of calculus 1, whose integral is, which is about the integral of a function from a to b, and you merely have to subtract capital F b minus capital F a, where the capital F is the antiderivative. That's the fundamental theorem of calculus. The second fundamental theorem of calculus says the following. FTC2 says, if you differentiate a function defined by an integral, then this is going to give you f of x. And it looks cryptic if you don't see an example, so let me put an example to understand what it means. But before I do that, I also want you to know that this just follows from the top one. Okay, so I'll show you an example first, and then I'll try to show you the proof. And the reason I show you the proof is that proof is actually more important than the statement itself. The statement itself is not so powerful. The proof itself is more applicable. Okay? All right, so let's try to understand what this is just by taking a simple example. So let's choose an ft. Give me an ft that's like simple to integrate. I'll choose one. How about 2t? Okay, 2t. So before we do that, let's see. We're choosing f of t as 2t, right? Then what's f of x? 2x, right? Because all that's changed is t became x. Right? All right, so we have that, and hopefully this is going to match with f of x, which is 2x. So we want this to evaluate to 2x. Now, why is that? Well, first, the fundamental theorem of calculus 1 says, what do we need to do? We find the antiderivative, right? So we find the antiderivative of 2t, which is t squared. And into this, we plug in x and 0. Oh, by the way, here, by putting 0, instead of a, I'm putting 0. Is that good? Right. So I'm making two choices here. To understand this, I'm choosing a to be 0 and ft to be 2t. Okay. And then with that choice, this theorem seems to say that I better get 2x as the answer. If not, then this is wrong. Okay. All right, so let's continue. d dx. X goes into t squared. What do you get? X replaces the t. So what do you get?
1/3 t.
No, you're not integrating. No, x just is. This simply means x goes into t. So you get x squared. And then 0 goes into t. So minus 0. Now let's think about what this means. What does this mean? This is just a fancy way of saying derivative, right? It's Leibniz notation. Don't be freaked out about the notation. It just simply means differentiate. Relax, okay? Relax, it's just differentiate. What's the derivative of x squared?
Relax.
Yeah. What's the derivative of x squared?
2x.
2x. Oh, so we verified it. It's true, right? It's true, right? Okay. So from this example, not only we see that it's true for this specific one, but we seem to have some understanding of what this means, right? Now let's actually do the proof. You can actually go in two different ways. Although I didn't explicitly state it in the very first class when I explained the fundamental theorem of calculus, what I really did was I explained this one first, and from here I deduced this. Okay? But if you accept that this is true, then now you can use this to prove this one. And the purpose is not to trust us, trust this. We know that it's true, but the way we prove it will be useful. Okay. All right. So let's actually do the proof. By the fundamental theorem of calculus, in the first part, it says we should first find the antiderivative of f, which we denote by capital F, right? And then we have to evaluate at x and then a and subtract. That's from FTC1. So from here to there, we're using FTC1. Oh, sorry, this should be x. Why didn't change? Now, here's a question. Again, this just means derivative, right? So you have to answer two things. What's the derivative of capital F of x? What's the derivative of capital F of a? Right. So first question, what is the derivative of capital F of x?
F prime x. Oh, wait, no.
Small f of x, right? Yeah, because by definition, what is capital F? That's the antiderivative. So if you differentiate f, you better be getting your f of x back. So far, so good? Okay. Now the next question is, what is the derivative of f of a? Aha, you think you should be getting small f of a, but that's wrong.
Well, the other one is 0, so would that be 0?
The answer is 0. But that's so puzzling. Let's think about this for a moment. Okay. Yeah, you have an answer?
Because it's a constant.
It's a constant, yeah. If you plug in a, you end up with a constant. Okay. So here's the thing. If you take, say, x squared, okay, and you integrate this, whose integral is 1/3 x cubed, right? And let's say we plug in x equals to 1, and then differentiate this. And here's another one. We could also differentiate and then plug in x equals 1. Okay. Let's see the difference. Here, what's happening? You plug in 1, what do you get? This is 1/3. And then you differentiate, what do you get?
0.
0. What about this one? You differentiate first, right? What is that? X squared. And then you plug in 1. What do you get?
1.
1. So there's a genuine difference between the order of operations. Okay? And this one is you plug in first and then you differentiate. Yeah? If you plug in first, then you get a number, and therefore if you differentiate, you get 0. That's what you have to know. Okay? All right. So notice that f of a prime is 0, whereas f prime of a is f of a. That there's a distinction between the two, as demonstrated by these two things. Is that good? No? It's still puzzling? If you differentiate first, it's a function, and then you can evaluate it, right? But if you plug in the number first, it becomes a constant, so you always get 0 if you differentiate.
Which one's the right one to do? You plug it in first.
So the correct one is we plugged in first and then differentiated, so it must be 0. It's this case. Good? All right. And that's the proof. That's what we wanted to prove, right? We want to show that this is equal to f of x, and indeed it is. So that's the proof. Okay. Now, I want to show you why the proof is more important than the formula. I just erased the formula because sometimes you may use it, but it's basically useless. So let me show you an example. And this could be a question on the exam. Let f of x be defined as integral from 1 to x squared of e to the t over t dt. And the question is, find f prime of x. So here's a very weird kind of integral, but it is a function, right? Because if you plug in a value for x, you can definitely find this integral and then plug in the endpoints and then you can find the value, right? Except that if you actually try to do the integral of this, you wouldn't be able to do it.
If you have to do that, it's just.
You can't do the antiderivative of this. So let's see if you can do this. Now, a totally wrong approach would be just integrate the top, integrate the bottom. That's a no-no, big no-no, right? That makes Dr. On mad, right? I just give you a scare here. So if you think about other ways to do this, what other ways can you think? Yeah.
Can you just make t into t to the power -1?
Okay, so if we rewrite this as t to the -1 e to the t dt.
That's just all I know.
And then what else can you do?
Integrate to back 1.
Okay, and then by parts we put plus minus d integral t -1
Wouldn't t
and
keep
then
going on?
e to t. It's
You can make
not
it
going to
u.
stop, right?
You make it u.
Huh?
You make t -1 u.
Oh, okay, that's another nice approach. What if we say u is equal to t -1, which is like 1 over t, so that du would be -1 over t squared dt, so that dt would be negative t squared times du. And then this one will be integral of t to the -1 e to the t times negative t squared du. So you still have like negative t -1 e to the t du. T positive. Because t squared times t to the -1 is t to the first power. But then you can't have t's. They have to be replaced by u. What do? You have to solve for t, right? So you think of this as u over 1 equals to 1 over t. If you flip both sides, you get 1 over u equals to t over 1. So t is 1 over u. So this becomes 1 over u. This becomes 1 over u. Yeah, unfortunately, it's not any better than before. Okay? And you can even try other things, like maybe set t u as ln of t. Then du would be 1 over t dt, which is exactly this part, right? So that'll be, but then t is e to the u, so this will become like e to the u of du. So it's not going to work. And imagine that this is an exam question, and you're doing this during the exam. That'll be horrible. At some point, you're going to raise your hand and say, hey, did you make a mistake in this question? I can't do the integral. It seems like an undoable question, unsolvable question. And then I'll just stare you down and smile. And you should be worried when I smile at you, right? So that's what's going to happen.
Should be worried right now.
Yeah. Huh?
That's what we should be worried right now.
No.
That was one of the questions on the exam, and I did that exact thing.
Oh, no. That was not the question of the exam. It's different. If you want to go over the exam with me, come to my office at 4:30. I'll help you out. It wasn't. Yeah. So what's happening here? And that's exactly what's going to happen on an exam. I'll put a question where the antiderivative is impossible to do. On the other hand, if you protest that, oh, that makes this definition impossible to calculate, the answer is wrong. You can still find the approximate value of this function for any value of x, right? I mean, for example, let's start with the easy one. What's f of 1? It's the integral from 1 to 1 of something. What would this be? If you integrate something from 1 to 1.
No, 0.
It would be 0 because it's like some antiderivative minus antiderivative of 1, so it will be 0, right? So it will be 0. But then what if we do f of 1? F of 1 with f of 2. F of 2 would be integral from 1 to 4 of e to the t over t. What about this?
E to the 4.
Well, you can't find the antiderivative, so you can't get the exact value, but you can still find the approximate value of this. How do you do it?
Substitute.
Not substitute. We learned methods. Come on. How do you find the approximate value of an integral? Not exact value, approximately. How do you do it?
Riemann.
Huh? Riemann sums. Yes, yes. Riemann sums. You can use Simpson's rule or midpoint or whatever your choice is, right? And if you have fine enough rectangles, you can find the approximate value. And if you want better approximation, you can use a computer to have like, instead of using like 4 rectangles, you can make 1 million rectangles to find a very good approximation of this value. So this is indeed a good definition. It is defined. So asking for this question, f prime of x, is indeed a legit question to ask, because you have a well-defined function, and the question is like, what is the rate of change of that function? That's a legit question to ask, right? And then this cannot be solved by just using the fundamental theorem of calculus, because this x squared just destroys it. This makes it bad. Okay? So now what do we do? Well, here's the idea. Solution. Define f of x to be the antiderivative of this. So I guess more like plus. And that's the beauty of algebra, right? And when you first went into the algebra class, you learned that you can have x for things that you don't know, right? You just name it, you give it a name, and you pretend that you know it. It's just like the fake it till you make it kind of game, right? You just assume that you know it, and then you just play with it, and at some point you actually get to know it, right? So just fake it. Let's say we do know the answer. We don't. By the way, maybe I failed to stress this. There is no way to find the antiderivative of this. Okay, even if you use like Wolfram alpha, you put that in there, it's going to spit out something that you've never seen before. It's the thing is. Our vocabulary of functions is very limited. Like you have exponential functions, trig functions, inverse trigs, logarithms, and polynomials, and you can add them, subtract them, take ratios, or you can put one into the other. There are only finite things that you can do with it, and those often would fail to describe a function well enough that sometimes you might be able to write something, but the actual function escapes our vocabulary. That could happen, right? That's why we're just naming it, okay? However, somehow by magic, though we can't know what this f of x is, we can know its derivative. Yeah, it's kind of amazing. And that's what fundamental theorem of calculus 2 is about, okay? All right, so now once so back to the fake it till you make it game, okay? So what you do is 1 through x squared e to the t dt. Okay. So it's like, what is this? Oh, it's f, capital F, right? I'll assume that you know what that is. Okay. Everyone here knows f, right? Capital F? Yeah. Now everyone knows f. So what do? You evaluate this f where?
X squared.
X squared.
Yeah, minus f big F. But then that would cancel out because it's a constant.
And that's your small f of x. Sorry, I'm using small f of x for something else. It used to be this as ft, but this is totally different. Maybe we should have named it as g of x. So anyways, let's say we have this. And what's the question? We're trying to find the derivative, right? So what you're doing is you're trying to differentiate this. Okay? And that's why I'm saying this way of thinking is important, not the formula. Just throw away the formula. Is really this way of doing things. Okay, now let's try to ask, what is the derivative of this? Derivative of this big F is small f, but unfortunately that name is reserved for something else, right? So let's call this g of t. And really, because capital F is the integral of g of t, you get what I'm saying? Yeah. If you differentiate f, you get what? G of x. Okay. So you're going to get g of x squared. But wait, there's x squared inside. You have to do something else. What do you have to do?
Differentiate.
Using, when you differentiate, there's something, chain rule. If there's an inside function, you have to use a chain rule. So outside, what do you multiply?
2x.
2x, because the derivative of x squared is 2x, right? Minus, what do you get if you differentiate f of what? 0. Remember, that's a constant. We just had that discussion, right? So that's it. Oh, but what is g of x squared? Well, this is our g of t, right?
So we plug that in.
So you replace all the t's by x squared and you're done. So it's e to the x squared over x squared times 2x. And it's a choice to simplify, but if you cancel the x's, one of them, you get 2e to the x squared over x. So that's the final answer.